can continue. So you can imagine if you have got say in three-dimensional space, which is the one most of us can visualize nicely. So there will be coordinates x1, x2, x3. So if you get two one-dimensional subspaces, so it's something like that, and another one here, then of course you can imagine that there is the smallest vector subspace which contains both of them, and that's the one which is got as the plane going through the origin, and it's spanned by the two lines. And this is the way how we sum the subspaces. So you see that's the general definition, and you can sum the subspaces this way. And we already told what is a basis, right? So the basis, of course, is each of the vectors in the basis span a one-dimensional subspace, and the whole subspace V is spanned by these one-dimensional subspaces. So in the R3 we can see that you have got say the plane, which is spanned by x1 and x2, and then you add the x3, so you will get a line and a plane. So it's already, if it's not degenerate, it spans the whole thing, right? So that's obvious, but there is one special feature, and the special feature is that there is a unique decomposition of each vector W from V as a linear combination, as a sum of vectors in these individual spans, right? So we have simply the three lines x1, x2, x3, and for each vector in R3 you can find exactly one choice of the coordinates x1, x2, and x3, which gives you this very vector, right? Because we have fixed the basis. So in our case there we fixed the three EIs, right? E1, E2, E3. So in general, if you are in an abstract vector space, choosing three vectors E1, E2, E3, which are linearly independent, and the vector space is three-dimensional, you simply can draw the very same picture. So you can always visualize it in your favorite coordinates this way. There is no difference. It's just the matter of choice of the coordinates which makes the difference, not anything essential, right? So this is the way how it works. And now there is an important theorem which says that in the abstract vector spaces everything works exactly in the particular k-n's, right? So the n tuples of coordinates. So if there is a finite set of generator, so whenever we fix some finite set of generators, so it's finitely generated, then there must be a basis, right? And here is the point where the fact that we are working on the fields of scalars is absolutely crucial. If we worked over integers, this theorem wouldn't be true. And actually in the proof, I will not go through the proof in this motivating introduction, or I hope at least it's just giving you some motivation to read through, or some additional, say, possibility to think about what you read before, whoever does it this way. So this is called the Steinitz exchange lemma, and it's something which is proved in the proof of the theorem, and it's much stronger result, because it says that if you've got a finite basis, so look, I'm underlying, I'm using the V for the name of the individual basis, and I underlie it. And that means that V is a set of V1, V2 up to Vn, right? If it's not a finite basis, then we can also think that you have a set which is the basis, and then the vectors are something like mappings from this set to coordinates, right? Right. So what I wanted to say, or what's written in the Steinitz exchange lemma, is that if you happen to have a finite basis V of vector space, and you pick up any number of independent vectors, linearly independent vectors ui, then we always can find exactly as many vi's to be replaced by the ui's, and it will be again a basis. So if we draw it in the picture, you see if I pick up some arbitrary vector in the R3, so if I do it in this completely independent way, I can replace every one of the E1, E2, E3, and it will again make a triple of independent vectors. But if my new vector would be, say, in the plane, if it would be somewhere here in the plane x1, x2, then of course I have to be more careful, but still it's okay. And I can replace anyone. But if it was a linear multiple of one of my vectors, then I have to be careful, because then if I replace some other one, so if I replace it wrongly, no, I'm wrong now. What I wanted to say, if I take it in the plane x1, x2, then I have to be careful, because I can't replace E3 with that one, right? So this one does not replace E3 with exclamation mark, right? Because I have simply replaced something which is independent again, right? So that's the point. And that's very strong, the Steinitz lemma, because actually only when we see the Steinitz lemma we can claim that every two bases in finite dimensional vector space have always got the same number of elements, and therefore our definition of dimension is correct, right? It can't happen that you have different number of linearly independent sets which would generate the whole space. Again, once we would work what's called modules instead of vector spaces over rings of scalars, so for example taking integers, this wouldn't be true, right? And you can then have different number of generators, and we shall be meeting these things quite often, right? So therefore I'm stressing this beauty and importance of having vector spaces as something like modules over fields. Right, so the second consequence is that whenever we start with some linearly independent set of vectors, we can always complete it to a basis, right? Because that's a straightforward corollary of the Steinitz lemma. And we can say that in this way a basis is simply a maximal linearly independent set of vectors. I'm all the time speaking about finitely generated vector spaces now. And it's at the same time, so it's maximal linearly independent set, and it's the minimal set of generators. And all of these conditions are equivalent. Right? Now, again, a direct consequence of what we know already about the basis is that whenever we have got a few subspaces, then of course if something is subspace in some other space, then the dimensions must be related this way, and they are equal if and only if the dimensions are the same. So there is no excuse, there can't be any gaps, right? So that's very important to know. And another nice thing is that you can count the dimensions for those W1 and W2 where you don't have the property of the summing independent vector spaces. Yes, so I didn't tell before, we are using plus for general vector space addition, and we are using different plus for what we call a direct sum. And this is when the intersection of V and W is 0. So if they don't have any intersection, it's a direct sum. And that's exactly what we saw on the one-dimensional subspaces generated by the basis vector spanning the whole thing. So that was a direct sum. And therefore, if you have a direct sum, every vector decomposes uniquely into a sum of one in V and one in W. And here what you can do is you take the intersection, that's here, and you see that if you add the dimensions of the two spaces W1, W2 in general, then at something like if you take say two planes in R3, right? So they intersect in one line. So if they are in the general position, they will generate the whole R3. But 2 plus 2 is 4. So you have to subtract the dimension of the intersection, and that's exactly what's written here. Right, and this is what leads us to the coordinates. And the last thing I want to mention in this week of MD A101 is what are the homomorphisms, right? I don't want to go too much further to coordinates, but what about morphisms? That's a general thing everywhere in mathematics. If you deal with some concepts, so you get much more information about the objects you are looking at by knowing how the morphisms which preserve the important structures are looking. In our case, if we have got two vector spaces, so what will be our morphisms? It's from Old Greek, so something which preserves the shapes, right? Morphisms. So it will be mappings between the vector spaces which preserve linear combinations. Right, so if I have something like A1, U1 plus and so on, AK, UK, that's a general linear combination, K scalars, scale vectors, then I just add the scalar multiples together, then I throw F on this, then this must be the same linear combination of the images, so A1, FU1, plus and so on, AK, FUK, and the brackets here, and that's it, right? And I will finish this week by noticing that we do have one such linear mapping always, right? Whenever we fix a basis, so that's here. So if we fix a basis of our vector space V, so finite dimensional vector space, then as I already told several times, every vector is expressed in a unique way this way. And so I can understand a basis as a mapping. So it will be V underline, and it will be a mapping from V into coordinates, right? It's an n-dimensional space, and this is the mapping I get here, right? So for every vector which is expressed as a unique linear combination, I get the n-tuple of the scalars, and that's the coordinates. So assignment of coordinates to vectors means exactly taking a linear map, because of course by the very definition, if I take a linear combination of the W's, then the linear combination just will show up here, and because we know the axioms of vector space, so it doesn't matter in which order we sum, so we can reshuffle them to put together those we need, so those with the same basis vector, and then we have the distributivity, so we add the coefficients. And here you see how important it is we are in the abstract level, right? Because we know the axioms, therefore it works. It's not handling n-tuples of coordinates. Now we are handling abstract vectors. But in the end of the day, it happens to be the same. So, right? So this is what we say, that choice of the basis is not only giving us the morphism, giving the coordinates, but it actually saying that it gives us an isomorphism, V isomorphic with K to N. So actually the new abstract way of viewing the vector spaces is nothing new, it's exactly the same one as the old way, the n-tuples of coordinates, except we need it that it's a vector space, so it's over field of scalars, and second, the isomorphism is dependent on the choice of basis, and that's a very crucial thing, as we shall see in the next weeks, because choosing nice basis gives us nice way of writing down the every linear map or other objects, and this help us to understand the properties and solve problems. So that's it for this week.